and there is a specific query about how to find the geometric multiplicity of matrix using eigenvalues. I will take that up, but before that, if you have any other query, so you can raise your hand. Someone was raising their hands for hand perhaps. I just missed him or her. So if you have a query here, you can raise your hand. Otherwise, I will start with that. Another query or you can say it's a doubt that was posted in the Teams channel about Q1B question number 5, whether the xs by fs transfer function was also required to be found out. It was not mentioned in the solution. So if you have found out, that is fine. So and I think that it is also required to be found out, but it's upon the TAs how they will give the marks. They are giving it for only ys by fs or both of them. I am not very sure of. So they will were you trying to speak something? It was background noise was coming. If you are not trying to say anything, then it's fine. Otherwise you can speak out.
No, sir, I have just joined, so
Okay,
my
no problem.
mic was not muted.
No problem. Okay. And that xs by fs is very easy to find because the xs by ys relationship is quite straightforward from the second equation in that problem. So it is not difficult at all. So if there are no other query, let us jump into the eigenvalue query. So I know that you are to submit the Jordan forms where this is required, important, but still I would try to help you out because this is a difficult concept, and like it can be difficult for many of you. And so let me try to see if I can uh, again uh, like discuss on this issue and resolve any query there. So the specific question is how to find geometric multiplicity of a matrix by using eigenvalues only. Okay, so of course you will be needing the eigenvalues, and you will be only needing the eigenvalues. So do you mean that you will not use the column operation? So what do you actually mean here by only the eigenvalues? If Vikram is here, he can unmute himself and try to explain what he wants to actually, what his query exactly is. Otherwise I will go in a general manner. So when you have a matrix A and you have found out its associated to it, you have found out its eigenvalues. So lambda I you have found out. Okay, and since we are talking about geometric multiplicity, so so here these are repeated eigenvalues, so there is at least one repeated eigenvalue. So let us denote that by simply lambda. So lambda be the repeated eigenvalue. So there are other eigenvalues also, those are not repeated. Suppose the lambda eigenvalue is the repeated eigenvalue. So now you have to you have the problem of finding out the geometric multiplicity. Now the geometric multiplicity is basically the dimension of the null space of this matrix A minus lambda I. This is true for any lambda actually. It may not be repeated also, but when you don't have repeated eigenvalue, then the answer is straightforward. The answer is that dimension of this null space would be 1. Okay, the dimension of the null space of this equals to what is, this is equals to basically the geometric multiplicity of this eigenvalue lambda. In case of not repeated or non-repeating, or what should I say, single eigenvalue, something like that, non-repeating lambda, then mg lambda will be equals to 1. Okay, what does this mean? This dimension, this also gives you the number of basis vectors of this space, null space of a minus lambda I, and these are nothing but, we also refer this as the eigen vectors, the eigen vectors. In case we have non-repeating lambda, then there will be only one eigenvector, one non-repeating, then eigenvector will be only one. However, if your eigenvalue is repeating, so that means your algebraic multiplicity of the eigenvalue, so your algebraic multiplicity of lambda, if it is greater than 1, if it is repeating in nature, then your geometric multiplicity, what that will be, is a question to be answered. It can be 1, it can be more than 1 also. Okay, so now this does not become a trivial question anymore. Now this becomes actually a problem to be solved, and while solving this problem you are basically finding out a lot of things. What you are finding out? You are finding out the number of basis vectors of this space, and you are finding out the eigen vectors. Okay, the eigen vectors, same thing, the number of basis vectors of this space is also, these basis vectors are also the eigen vectors. Now this could be only one, so for repeating I really don't know how many are there. So if I have the algebraic multiplicity as 2 and I have geometric multiplicity also as 2, that means the eigenvalue is having 2 eigenvectors, and I am good, so I don't have to find any additional eigenvectors. But if my algebraic multiplicity is 2 or 3 and I find that my geometric multiplicity is less than that, value 2 or 3, whatever that value, then I have a problem. So if your mg lambda is equals to ma lambda, then all eigenvectors are the basis vectors of null space of a minus lambda I. Then all eigenvectors are basis vectors of a minus, null space of a minus lambda. The problem happens when mg lambda, the geometric multiplicity, is less than the algebraic multiplicity. Then the problem happens, what problem happens? You will get less number of eigenvectors than there are repetitions of eigenvalue. That is the problem. What does this mean? This means that in the vector space you are able to find out only a few such vectors along which if you start you will stay in that line. So that is the special property of these eigenvectors, right? So you are able to find only a few number of such vectors. Normally you should find n number of such vectors for a n dimensional space, but now you will find less than n number of such vectors. So what about those additional vectors which we have missed? That we need to find out by doing some additional work, and that additional work is what we have shown in the lecture videos, that I will again illustrate here. Okay, what we need to do. So I don't have a ready example which I can go about. Let's see. But in all these cases you only need the eigenvalue. Please note this, you only need the eigenvalue in order to solve for the eigenvectors. So the problem is that my mg lambda is less than ma lambda. So when you are trying to find out the number of basis vectors of the null space, the first thing you have to do, the first step is to evaluate a minus lambda I, and you will find it to be some matrix. Now it will have some columns, so this will be some columns C1, C2, C3 like that up to Cn. Now you do the column operation on these columns. So here is the identity matrix to start with, and you will do some column operations. So after doing some column operations you will eventually come to the last step where some columns will be 0 columns. Suppose there are some non-zero columns and some 0 columns. So like that. So these vectors which are coming at the bottom of the 0 columns, they are the basis vectors of the null space of A minus lambda I. They are the basis vectors of the null space A minus lambda I. However, the question is that which of these, like they will form actually one of these or a particular combination of these will form the initiating vector of the entire chain of generalized eigenvectors. So there, because let us take 2. So suppose there are only 2 number of 0 vectors here, and your ma lambda is greater than 2 obviously, because this is mg lambda. This number 2 is the mg lambda, right? This is the geometric multiplicity. So ma lambda is greater than 2. That means whatever be ma lambda, suppose it is 4 in a particular example. So you have to find out additional 2 vectors which would also be the eigenvectors, and these additional 2 vectors are referred to as the generalized eigenvectors, and they would be the basis vectors of generalized eigenspaces. So how do you get these generalized eigenspaces? You don't restrict yourself to a minus lambda I, you have to go to a minus lambda I square, then perhaps to a minus lambda I cube, and actually you have to go till a minus lambda I k, where there is a concept of minimal polynomial. Your max will basically have x minus lambda's index as k, and there can be some other terms, there can be some additional terms, but when you have x minus lambda to the power of k, that means if you put a in place of x, this is going to vanish when x equals to a. So when you put x equals to a, so a minus lambda I k is going to vanish your minimal polynomial, and this order of k is up to which you have to extend the eigenspace. You have to go till that. And that means one of the original eigenvectors, either this one. So suppose this is the v1 and this is the 2. So either this or this is going to lead you to k number of eigenvectors. Either this or this, one of these is going to lead you to k number of eigenvectors. That means there is a Jordan block of size k. This is k cross k. So this thing, or that is the index of the repeating eigenvalue in the minimal polynomial, is giving you the size of the largest Jordan block. This has been proved in one of the lectures. I don't recall it right away, the proof, but this proof has been given in one of the lectures in the Jordan form module. First lecture in the Jordan form module, perhaps first or second maybe. So one of these is k. So one of the Jordan block is of size k. So from your mg lambda, from your ma lambda, which is the repetition of eigenvalue, you subtract this k and you get the remaining number of eigenvectors. Now we don't know, so suppose we have, let us take numbers, so it will be easy. So suppose this is a big number, suppose this is 6, then suppose your k is, we have taken here geometric multiplicity is 2, okay, geometric multiplicity is 2, that means 2 initiating eigenvectors are there. So that means there will be 2 Jordan blocks. So this is important, that the geometric multiplicity is giving you the number of Jordan blocks, and the index of x minus lambda in minimal polynomial is giving you the size of the largest Jordan block. In case your mg lambda is 2, then the problem becomes easy. because from mg lambda you will know how many Jordan blocks from x minus lambdas to the power of k. So you will know this k, you will know the size of the largest Jordan block. Suppose this k is 4, suppose. That means the other Jordan block is having size 6 minus 4 equals to 2. And supposing that this is going to lead me to all these eigenvectors, this particular vector is going to lead me to only one additional eigenvector. That eigenvector will be in this space. So in A minus lambda you are getting 2 eigenvectors, here also you will get 2, but here you will get 1, here you will get 1. And how to find these eigenvectors? That has been extensively discussed in the lecture videos. There are two methods, and the second method is a more general one, while the first method might seem easier for some people, but the second method is a general one, so one can go via that method also. And everything involves only column operations, nothing else. Only you have to do column operations, that's all. Now suppose that your mg lambda was free, so there is another initiating eigenvector. Then for this particular case it is easy, so one block is 4, so remaining size is 2 and remaining number of blocks is also 2. So what is the size of those blocks, you understand. So if this is the initiating eigenvector, then these two will be the eigenvectors of the remaining blocks, this one and this one. However, if your ma lambda is or let us reduce k, suppose your k is free, in that case remaining size is free, and you have two blocks, and this is also fine, one should be 1 and another should be 2. So actually the problem will happen if your k is 2, we have to change this actually. Let us see. Suppose this is 7 and you have 3 here, 4, 3, yes 3, then one block, the largest block is of size 3, the remaining number of eigenvectors to be found out is 4, and you have 2 initiating eigenvectors for that. Now one block, what is the size of these blocks, we cannot be sure of in this situation, we absolutely cannot be sure of, because it can be 1 plus 3 also, it can be 2 plus 2 also. So we have to actually go via the route of generalized eigenspace and see where it leads us to. So the general rule of finding out the generalized eigenvectors and the generalized eigenspaces, how to form the generalized eigenspaces and go about finding the generalized eigenvectors is of utmost importance, especially the algorithm number 2. The algorithm number 2 is very important, and I would not repeat the algorithm number 2 here right now, it is off my mind also, I have to look into my notes once, and it is already available in the notes. So I have given 2 examples if I remember correctly, so you go through those 2 examples. do a few problems. The tutorial problems are already there. Do a few problems and you will get a hang of it. It is not, it is only a step by step process. However, conceptual understanding I have tried to clarify once more. If there are more thing that you want to understand, something that is still missing some clarity from your side, then you ask them. Right now you can raise your hand, or if something crops up in your mind later on, you can ask me question then also. So I have already put up a survey which is an anonymous survey, so there also you can put your question if you don't understand something related to the first 3 modules of the course. Next module also I will put up some survey in some time. So I rest here and I wait for your uh, queries if you have any. So no hands are getting raised, neither there is anything coming in the chat. So I hope that you have come to understand this portion, and by doing the tutorial I'm sure you will get a quite a good exercise on this, on quite a good practice on how to find out the Jordan forms. Okay. So if you don't have anything else to ask, then I think we can end the session. So you see again, just if you have anything cropping up in your mind.
Thank you, sir.
Okay. So who was this? I didn't know anyway. So thank you for your appreciation, and so I think I can end the session now. And as I told, so any further query you can post, and I'll be happy to resolve. Okay. Thank you.